speaker is Alessandra Sciutti, who is a tenure-track researcher and head of the contact unit of the Italian Institute of Technology. She received her bachelor's and her master's degree in bioengineering and a PhD in humanoid technologies from the University of Genova in 2010. And in 2018, she was awarded the ERC starting grant Whisper. And her research mainly concentrates on the sensory and motor mechanisms that underlie the mutual understanding of human-human and human-robot interaction.
Thank you very much. Let me try and share the screen. It's a great pleasure for me being here today. I extremely enjoyed the keynote and the former presentation, and I hope what I will be discussing a bit today can be connected, can add up a little on the beautiful results and points that were made by the former speakers. So thanks also for the presentation. And today I want to, let's say, ask myself and others a question that we often have to face when we are discussing on what we want to do with our robots. We want them to be cognitive, but how much do we want them to be like us? So let me start with what I usually present as a goal of our research in the contact and in the RBCS unit. So to create more humane robots. We often say that what we do is for this particular goal. And an important point that I want to make is that for us, more humane doesn't mean robots that look more like humans, but that see more like humans, that perceive the world more like humans. And why is it so? Well, because it is true that we have clearly seen in the past time and even recent times incredible advances both on the dimension of artificial intelligence and the competence of our computers, but also at the same time advances on the physical abilities of robots. And here I'm putting just humanoids, but of course it expands much more if you consider robotics at large. So these are great advances that make people expect and hope to really have soon robots that can do our dishes or anyway live with us in our houses with no big difficulties. But then this is relatively old, but still maintains its validity. When we are actually facing robots with general settings, and especially with general settings that entail interaction with humans, unfortunately, expectations are not met at all. And we see unexpected failures. And I think that also Tony showed it very nicely for an application that was not robotics only related, but AI related, that, of understanding language. So what we want is to actually move next. So stop having robots that are very complex and able tools and move to a scenario where they are actually our cooperators, our helpers. And every time we try to do this jump, what we face is a sort of new version of the good old Moravic Paradox. So if on the one hand, some tasks look very difficult to our eyes, I don't know, winning chess, learning to play Go, winning StarCraft, they are comparatively much easier to be ported on machines than the equivalent of the abilities that a child has. So recognizing a face, pay attention to the things that are actually interesting to a human, I would say. So we always face the need of doing a leap, an actual leap though, from competencies that are on the bodyware and on the mindware and extremely exalted to competencies that we expect, we give as granted, that are the ones by which children can get together even before learning to speak and cooperate on a game, on a task together without any big problem. And this actually is an important step, and it's a difficult step. So on this very specific step, the most expert in the field of machine learning are interrogating themselves. So you can see Benjo, Josh Benjo, Jan LeCun discussing it and suggesting that yes, neural networks, deep learning, and artificial intelligence have made big leap in the past, but still the ability to generalize from few examples, for instance, that the children exhibit very naturally is still unmatched. I recently attended this very nice talk by Joshua Tenenbaum at Developing Mind series. And again, he was underlying this gap. And an interesting point that comes out if you read or listen through this intervention, and I heard it come up also in today's talk, is that often the missing element seems to be the common ground. So something we have as humans and that we leverage upon to establish mutual understanding, to facilitate cooperation, but that is actually fully missing yet in machines, be they computer or robots. And I think that that's an interesting insight, an interesting perspective to look at. On the other hand, this forces me from a robotics perspective to ask, where should we start from to look for this common ground? And one possibility, according to me, one roadmap that we can follow is to try and see what is the common ground among all humans. And this is what I'm trying to, identify in three little steps today with you. So I think that the first approach, a first step to building a common ground, a shared vision from humans and robots, is to look for what I called humanization, but by which I mean enable the robot to be considerate of how a human perceives, of how a human senses the world, of how a human thinks. And to do that, you as a designer, you as a developer, have to do a lot of work in terms of adapting the system. So both it's in its shape, but also in its behavior and in its sensory and motor competencies. But that's not enough. And I think this ties in very well with what was presented before by Yanis and Tony, because it's true that we share some commonalities among humans, at least some sensory motor rules that are really shaping the way we think. But on the other hand, each of us has its own differences. So we have inter-individual differences, and we are not static. So even if I have, let's say, a steady personality, my internal states vary all the time as a function of the context, as a function of the situation, of the task. And this is where the designer cannot do anything alone, because it needs really the robot to be able to adapt through learning and adaptation and personalization to the partner. But, and I think that these two components already make a big portion of the story, but they are not the full story yet, because then, and I will advocate for that at the very end of the talk, it's also very important to start thinking also on the dual side of it. So whether it makes sense to have a full adaptive agent, or whether we want or we need to have it have its own identity. And this ties a bit with the discussion about pretense and faking that was very interesting and that popped out during the discussion in the past few discussions. So before entering into our discussion, let me drive through each of these steps with more details and also a few examples. So first of all, the first step, according to me, is to really endow the robot with the ability to sense like a human, or if not directly sensing like a human, being aware of how a human perceives. And this comes from very seminal intuition, if you want, in the field of HRI, where it came out by Cinzia Breazeal's work, by Brian Scasellati's work, where it was pointing out very clearly that to facilitate an automatic understanding with an agent, well, it is so much easier if the agent finds similar interesting or similar things interesting, or if it has similar sensing properties. And if this is true, and I definitely think it is, we need robots that are aware of how we perceive, and therefore we need to have a very clear understanding of how humans perceive. And human perception is really challenging because, of course, most of this happens below our level of awareness, but our brain transforms our senses, transforms the world for us. So, in general, perception is really a form of inference whereby I take the input that come from my senses, but then the brain enriches it, transform it by using information coming, for instance, from my prior experience. And this happens all the time, but I'm aware of that entire process only when it goes wrong. So, for instance, I realize it very well when we are faced with visual illusions. So there I realize that my brain is inputting information, is filling gaps. But this is happening continuously. And this is done because it's beneficial. It allows me to understand things that otherwise, with the only information coming from the senses, I could not grasp, I would not be able to handle properly. And this doesn't happen only at the level of perception, it happens also at the cognitive level, where there are evidence of plentiful of cognitive biases. And these biases, which means I'm perceiving and I'm assuming things that are not real at all, are not a problem per se. Actually, it seems, and it has been suggested, that they are functional features. They are really needed by humans to, focus on what really matters. For instance, in face of limited memory capacity, or in face of a slow reaction time, or in face of multiple stimulation and incapability of dealing with them all, these kind of biases really help us to focus on what our brain thinks really matters for our survival and for our interaction with others. So this has a very strong implication. The fact that if we are putting together a human with all this wonderful machinery at work, and a machine which has very accurate sensor, we will end up having very different visions, having very different understanding of the world. And this is, of course, an obstacle for interaction. And I think that one example is really, crucial for our kind of task, is that of action understanding. Already today, it came out the mention to the role of the mirror neuron system, or the potential implication that it has in primates and in humans. But if you think of it, you have neurons, or a system that responds not only when you're performing an action, but also when you see someone else performing the same action. So in some sense, you have a sort of vocabulary, a direct connection between what you learn to do by yourself and what you're saying. So your internal models are somehow shaping what you perceive, what you understand of the word, of what others are doing. And this has the strong consequence that whatever action you're saying, you see it also as a form of communication. And this is the classical example. It's a simple act of passing an object. And what a machine can detect here is clearly a movement, if you see the video of it and not just the snapshot I'm doing. But what I'm seeing there is so much more than a mere movement. First of all, I see the intention behind Carlo's action. So Carlo wants to pass the object to ICOB. I can see the state, or let's say the attitude that Carlo has toward the robot. So is, well versed. It doesn't seem angry. And I also can realize something about the relationship between Carlo and the object. Because even though the object is not fragile at all, you can notice that Carlo is moving it with care, with two hands. So in a glimpse, without even taking the time to really think about what I'm doing, I had a very strong reading of what's behind this scene, or what are the motives that are pushing Carlo. And this if I were in the place of ICAB, would have allowed me to predict and prepare to perform the next action coherently. And this is something that we need if we want to humanize machines. And this is not a novel findings. Indeed, already Darwin pointed out very clearly that if we want to understand what others are doing, or even what others are feeling, actions are such a strong form of communication. The problem of really, porting this knowledge onto our machines is that it is so common, it's so natural to us that we don't know which are the mechanisms that underpin this ability. And indeed, if we look at human development, we notice that a bulk of the skills that are necessary at the perceptual level to exhibit this competence in reading others and being aware of how others perceive is there since the very first minutes of life. So newborns already are sensitive to the gaze direction of a partner. They are sensitive to faces. They are sensitive to whether the motion is in front of there is biological, so generated by a living being, or non-biological. So this is so strongly rooted in our brain and the way we behave that when it comes to port this ability on machines, we often give most of these abilities are granted, but they are not there in per se in an artificial intelligence. And here I believe there is the seed of a part, at least, of this common ground that is so often mentioned. A good question that sometimes is asked when I come up with the word humanize is, but what do you mean by humanize? So you mean that you need to have robots that are humanoids? And indeed, I'm using humanoid in my research most of the time. And the answer is, of course, it varies a lot, of course. There is not a unique answer because there are plentiful ways of developing robots of a lot of different shapes. And also, if you think of robots designed to facilitate communication and inspired by existing interaction patterns, you can imagine already the inspiration coming from animals, for which there is already in place a sort of type of interaction and a kind of language, also non-verbal language that works very well, and it's not dependent on the human form. But there are certain elements of the anthropomorphic structure, if not a full android form, that bear some interest. First of all, an anthropomorphic shape has a utilitaristic nature, so it really allows to easily, or sort of easily, manipulate and use the same tools that were originally designed for humans. Another aspect is that anthropomorphic shape, if it is paired with anthropomorphic inspired kind of sensing, really can help in facilitating mutual understanding. So let's imagine I'm talking and with someone, and at a certain point I realize you are not hearing what I'm saying. Okay, what I do is what this little guy does. So I go near your ear and I start speaking to you louder. But what happens if who's speaking, who's listening, let's say it's this robot. So the intuitively fixing issues when something goes wrong, well, the non-expert user will go for internal models that they have of previous interaction. And if you have a shape and a sensing system that recalls that of a human, that will be very easy for them to find a natural way to help the robot. Whereas with a design that is not so obvious, you will require participants to actually learn about how the system works. And the other aspect that, and for me, that is one of the central one, is that, and it is connected with the mirror neuron example I mentioned before, is that humanoid shape and humanoid motion have a special role in our brain. because we are sensitive to several of these kinematics regularities and dynamic regularities that are characterized the way we move ourselves, and that our brain is attuned to detect in others when they're moving. And so if you're using this kind of choice in the robot motion, then you know, or you have a good chance to trigger and tap into the very same mechanisms that work when we are interacting with humans. There is also a crucial and very general consideration that we can have about embodiment. So the way I can move my body and the way the body is structured really determines also my interpretation of the word. So if you see this baby, and let's assume that it is learning concepts, it will learn that, a corridor or a stairs will represent the category of passage because you can pass through them, whereas a wall will be an obstacle. But if you consider this poor robot there, well, for it, the possibilities of action determined by its own embodiment are quite different. So for this robot to learn the concept of passage, well, stairs won't belong to them, okay? So the fact of having different bodies and the fact of having hence different action possibilities can also represent a barrier in the building of shared representation when we move to language, when we move to more abstract representation. And this is another element that sometimes tips the point, the balance, sorry, to look at a human or anthropomorphic inspired kind of structure to facilitate the sharing of understanding between humans and robots. On the other hand, we all know that choosing an anthropomorphic shape might bear also negative consequences. And I'm just citing very briefly here the entire concept of the uncanny valley, the fact that if you try to imitate the structure of a human, but you fail to capture it fully, you might end up really in breaking the sense of affinity that the robot might trigger in the partner, and this becomes even more strongly heightened if motion is added to the equation. And this is often very nicely used in movie and video games to actually trigger the most uncanny scenarios just by playing around with a human-like shape and very non-human-like motion. So how to balance the need and the benefit of drawing inspiration from an anthropomorphic structure with the risk and the implication of being bound by an anthropomorphic shape, which is anyway quite limiting in terms of what a robot can do. So our vision is that this can be seen as a sort of two-step process. So at first, having an anthropomorphic body for a robot aimed to understand better human cognition, it could be beneficial. It helps us, bridging through the same embodiment, being able to use the same tools, create the same meaning, and trigger the very same regularities and neural activations that we see for human-human interaction. So we can take this benefit. But this is not the end game. As soon as we can be confident to have understood how the human works, so have a good model of how human thinks, then the next step is to enable a robot to relate with humans. And in a sense, this means to be aware of how a human body works and how a human brain thinks, but to the point that independently of the robot's shape, you can establish a natural interaction. So in this sense, humanizing can start or can benefit at the initial steps through passing by a humanoid shape, but this is just the starting point from which you leverage to try and build a general ability for robot of any shape to relate and be considerate of humans. And that's why we are using a humanoid robot, exactly because our first aim is really to understand how humans perceive, how humans act, and how human cognition develops, especially in the context of interaction. So if we're using the humanoid robot in our, let's say, avenue toward humanization, what we are doing? Well, we are especially focused on the mechanisms of embodied communication. So if we want to have a robot that interacts with us in a nice way, where us means a human being for the moment, not a specific one, it needs to be aware on how we relate with other humans. And so it needs to be able to sense the kind of messages we continuously send to each other while moving, and at the same time, communicate them in the very same efficient manner. And this is what we explored during our research with the iCub humanoid robot a lot. So using robots as tools, as probes to try and implement models of how humans move and communicate to see during a real interaction whether the communication is effective or not. And we explored several dimensions. This starts back in 2014. This was inspired actually by the works on mirror neurons and the phenomena of motor resonance. This is a work with Luciano Fadiga, one of the fathers, let's say, of the mirror neurons, in which we evaluated whether something that happens in human-human scenarios, so automatic imitation, I move fast, you move fast, I move slow, you move slow, is spotted, occurs also for humanoid robots. And this was interesting because there were simple action that we asked the robot to do, so moving object back and forth. And we noticed that as it happens for humans, also after seeing the robot movements, participants changed their velocity automatically without instructions to adapt to robot velocity. But the interesting point that came out was that this mechanism stopped as soon as the robot stopped to move according to biological regularities. So if the robot was moving, let's say, as a human with acceleration and deceleration, with a very natural passive movement, then humans adapted their speed to the robot very naturally. But as soon as the robot started to move at constant speed, so a very simple movement, but constant speed, non-human-like, inspired, then this automatic mapping that the brain used before stopped to work. And this is interesting because it tells us that the relatively small modulation of how the robot moves can change whether our brain reuses the models that we have for human-human interaction or not, and needs to learn a different way to interact with this new agent. And it's interesting because this kind of phenomenon of automatic adaptation is something that occurs also in less experimental scenarios. So when you are actually collaborating with someone, in this case, for instance, putting objects into a box together with someone. And we verified whether this kind of motor contagion occurred also between human and robot in this more naturalistic, so to say, scenario. And the answer is yes, there is a very clear adaptation. So if the robot moves faster, I move faster, and vice versa, when the robot moves biologically. And another interesting element that came out from this study that was done both in Italy and in Japan with the same platform was that even considering the very different cultures that exist in these two countries, especially in relation to the interaction with robots, well, this automatic adaptation, this mechanism was very similar in the two countries. So this suggests that this basic sensory motor coupling that we found and that we could reproduce with the robot is something very basic, and that withstand and exist even in presence of very different cultural developments. And we moved further more recently, not looking just at the timing of an action, but really to the style of an action. So The idea that whenever I move, even passing just an object to you, you're immediately aware if I'm kind and gentle toward you or aggressive. And we wanted to see whether even robots can, with the proper regularities in the emotion, express this kind of information, even without showing their face. So we worked a bit to try and port the style of an action onto the robot. And the results that you see some excerpts seem to be yes. So we were very happy. But the interesting element that to us was really astonishing is that when we went to look at the neural activation of participants in the areas that usually respond to gentle versus aggressive actions by humans, we could find with the robot a very similar activation. So the dorsocentral part of the insula, which is one of the major actors in the process, was activated similarly for human observation and for robot observation when the robot was programmed, designed, its behavior was designed to copy, to capture these motion regularities. And I have to say, this was not an easy task because with the robot, you have the opportunity to really play around with the parameters. No? So our first approach was saying, okay, what is a gentle movement? A gentle movement is a slow movement. And what is an aggressive movement? Well, it is a fast movement. So our first manipulation was to create a biological motion for the robot and just modulate its velocity. And then we asked people to tell us, oh, do you feel it is aggressive or kind? And people said, yes, aggressive, kind. So overt judgment looked fine. But when they went to look at the activation of the neural response, we found out that these two different types of action were not effective. They didn't change the way the brain activated. Then we moved on, we retargeted, we copied the signature of aggressiveness that we recorded from actors onto the robot. And only at that point, we found out that the neural activation was very similar. So this tells us again that we have to be very careful about the signature of motion because it can really change the way our brain treats this and enables or not to react appropriately. Because this has also a very strong behavioral consequence. Indeed, what we found out with an interaction experiment was that if the robot points at an object in an aggressive manner with this movement that I described, then you will move toward the object more aggressively. And this means that, again, even a little change in the simplest of action, pointing to an object, can really shift and change the entire dynamics of the future interaction with the robot. And very recently, we found out that this doesn't hold only for humanoid robots, but if you do physical interaction with a manipulandum, so a robotic arm, and this robotic arm gives you a perturbation, which is either aggressive or kind with this feature, you'll end up moving afterwards, either in a more aggressive or kind manner. And these are just a few extras of examples of how you can identify what matters in the context of robot motion and what regularities of human motion can play a role in changing the way human will understand intuitively what the robot is doing. And if this topic is of interest of you, I really warmly suggest you this book. We edited it not long ago. And it has a very nice collection of authors that address the question of why matters modeling human motion from 3 different perspectives. So from the field of motion perception in humans, so neuroscience, developmental science, to computer vision and machine learning in general. So action understanding, action segmentation, to the robotic point of view. So how can I design proper motion, for instance? So, and I loved how the different authors address this question in a very peculiar and specific manner. But of course, we don't need only to have robots move in a proper manner. We really need also them to be able to read the very same features in our everyday motion. And this is potentially even more difficult than the first part. So we started with the inspiration that comes from the earliest days of life. So the fact that children, newborns, can detect biological motion, and we ask themselves, how can we endow a robot with the same ability? So we started thinking of what makes special a biological motion, and we come up with the idea that maybe one regularity that is well known could matter, which is the 2/3 power law. The fact that the way we move along a trajectory, we don't choose randomly the velocity, but the velocity is somehow dependent on the curvature of the trajectory. And among all the possible ways to move, we always pick that one. So we draw inspiration for this, and we created a very simple ability for the robot to detect apparent motion and extract the features that were inspired by the biological motion rule I mentioned. So just velocity and curvature. And through a bit of machine learning and showing very limited examples, so you see Alessia performing some biological action, and on the lower line instead non-biological motion, like a balloon bouncing, a toy train moving. We found out that the robot could learn to disentangle biological versus non-biological motions. And just by focusing on those features that we believed were important, coming from the study of how humans perceive biological motion. And the interesting thing is that although we draw our inspiration from a very young child, indeed a newborn, the outcome of this algorithm is very powerful because it allowed us to overcome limitation from classical methods for activity detection. So we didn't need to have the full body visible. We didn't need to see the skin, for instance. But even more, we didn't need to see a human at all. In this example, Alessia, which is the human, is actually moving an object, but the robot is just seeing the stick, the object. But since the object is moved by Alessia, its motion captures the feature of biologicity, and therefore the robot can recognize it as a biologically moved and then reorient its attention and find the agent, which means that this system allows us to find activity detection even without the presence of a human inside. The other interesting aspect of this kind of work is that the destruction of these features, again inspired of how humans perceive features, allowed us to scale up and use the very same features for more complex tasks, from action understanding across different views, coordinating across different views, and more recently, detecting the way a person is moving an object and understanding whether it requires carefulness or not. So without knowing at all the nature of the object, the robot, just by monitoring the way a person is moving it, can infer whether it requires care or not. Of course, it's not enough to see the body of a person. We have very precious information about the reaction of a person by looking at the face. And so we develop different systems that enable facial expression, recognition, or imitation. And another precious source of information that also Yannis mentioned very well today was the gaze. Gaze is really very helpful in both understanding what the intention of the person is in the next future. And here the robot showed that just by monitoring eye-head gaze, without having to listen to what the person was saying, without even having to notice what the person was pointing, it was able to find the right moment to act and the right object to pass most of the time, revealing how rich is this kind of information. But also gaze can reveal further information. For instance, not just looking at the direction, but looking at the pupil size. It is possible to understand the level of cognitive load of a person, and this in turn can be used, for instance, to infer whether a person is lying or not. So, also from this point of view, we can say that these are examples, but there is so much to be extracted, let's say, or to be understood and sensed as soon as you know where this precious information lies. And this somehow depends on how we humans are built and developed during our childhood. And a robot that is actually humanized is a robot that can make proper use of these signals by understanding humans, sometimes without the need of speech or direct instructions, and that can choose and select the proper way of moving to be as transparent and comprehensible as possible. One assumption that might come from this first part of the work is that, we know models from studying humans, so why don't we just copy paste them on the robot and we are done? And for this, there is a big issue. And one of the big issues I just want to mention today is that we don't know whether some perceptual rules, for instance, are stable and are the same when we are alone, perceiving by ourselves, or when we are perceiving in collaboration with someone else in interaction. And indeed, we have recent results, I don't enter into detail just for the sake of time, that really show that if you are involved in an interaction, and you can replicate that with a robot that exhibit social behaviors, well, the rules that you follow to perceive even basic properties like length or time can be modified. And this implies that it's not possible for us to just take models that pre-exist in human studies, implement on robots, and be sure that they will work, because most of these will need to be put at test in a real, controllable interaction. In that sense, the robot is helpful because it allows you to realize the test while keeping control on what the robot do and what the robot feels or senses in the environment. And another important caveat on the other direction, as we cannot take directly models that come from humans and implement on robots and expect that they will work fine, the same holds starting from computers. So we cannot assume that rules that apply to automation and that we derive from human-machine interaction in automation naturally applies to robots as they are. And again, I won't enter into the detail, but we have several examples of these, and in not only our group, of course, for instance, in the context of trust. The way you reciprocate a robot is different than the way you reciprocate or you trust or you comply with a computer request. And another factor that is very different is that of failures. Failures in automation have an impact on trust that is different than failures that robots have. And this has somewhat to do with the kind of rapport that you build with robots, which seems to be different from that, the one that you build with the other kind of machines. So with this, I think I gave you a sort of big picture of what I mean by humanizing. So the first step, so creating robots that have the ability or the skills necessary to relate with humans, human beings. But of course, that's not enough. We really need to close the loop to be able to adapt to that human, to that person that is interacting with me today at the moment. And this cannot rely only on a wise combination or use of these signals, of this information. Actually, we need to create something more. And what we usually see is the need of creating an architecture. So something that combines the ability to act and the ability to perceive with other elements, like, and we heard of examples today, both from Tony and Yanis. So the idea of having memory, the idea of having an internal drive or internal stimulation prediction skills. And one thing that I want to clarify is that there exists already a lot of wonderful architecture in the world. There is a very beautiful review about the last 40 years about cognitive architecture, and some of them have application on robotics, and they're very nice. The point is that often the kind of assumption and human inspiration they are based upon is this kind of video. So a child driven by curiosity with a lot of sensory motor abilities that can learn over time a lot of things. But this kind of representation of a human developing is a nice one, but it's just very partial. Because if we look instead at how much time we spend in interacting by ourselves and how much time our life is actually a social life, we see that the social component is so important for us as human beings when we start developing. And this is not fully reflected in the vast majority of the architecture that are now out there. Of course, Hammer is a nice exclusion for this, so it is a nice exception. And as it is the approach in Spark, of course, is socially based. But these are wonderful exceptions in some sense, because if you look, for instance, at what are the core cognitive abilities that come out from this review, so those terms or elements that are more commonly represented in the cognitive architectures that have been reviewed by Kotzeruba and Sotos, you see that the elements that would be crucial in a social dimension, so either social elements, but even affect connected elements, are totally missing. And this is probably something that we have to think when we are creating our own cognitive architecture, possibly taking into consideration the change that have influenced recently other fields, like the entire idea of neuroscience that has moved from third person passive spectators perspective to perspectives called the second person neuroscience, so where the interaction is really at the core, and with the claims that are very interesting that for instance suggest that maybe social interaction could not be an ability that emerges from lower level cognitive function, but maybe it is the default mode by which we communicate with the environment. And let's say the lower level cognitive function, the individual abilities are side effects, which is an interesting view, and that might reshape a bit the way we start thinking about the future of cognitive architectures for robotics. And okay, so we want to have a certain cognitive architecture that allows the robot to close the loop, to use action and perception, but at the same time to enable adaptation and personalization. And again, just a very fast review of examples where this matters. So we mentioned about reading facial expression. Facial expression can be very useful even in the context of rehabilitation or assistive robotics, to have a sense of how the person is living the experience. So this way, the robot could couple the measuring of the performance of the participant, which is of course very important in the training, but with a sense of how the person is reacting, if how much it is they are engaged, how much they find the task challenging. And we realize, for instance, that even just by monitoring facial expression, it is possible to notice when participants are really facing a very hard challenge, with an unexpected increase of valence as people start to sort of laughing or smiling at the difficulty. And again, we mentioned about the cognitive load before, monitoring the pupil size to understand when a person is lying or a person is experiencing a higher cognitive load because they are creating a story, something new that didn't exist. And also this can be put within a small architecture to enable the robot to progressively guess and adapt over time its performance, getting to know exactly how that particular person reacts to cognitive load, and improve its ability to understand the partner, just knowing its own or their own specific dynamic. And this is interesting because then, beyond understanding a lie detection game task, it can be also used to have a sense of whether a person is facing a risk and how they are treating the risk. And at the same time to have this information so that the robot can choose and adapt its behavior to be either a friend that let's say try to push the participant in the right direction, or even try to use it as a fake foe to try to investigate the risks posed by social engineering by combining the information that come from the pupil side, for instance, but also other information coming, for instance, from the way the person give their response or their physiological responses. And these are very recent results that we found out that suggest that indeed, by monitoring this kind of signal, it is possible for the robot to have a guess, a reasonable guess of whether the person has really understood that there is a risk ahead, that it is a social engineering attack or not, and even predict whether the person is going to accept the risk or not, in order for the robot to select then the most appropriate way to guide the action of the person. Beyond sensing and helping the partner, it's also interesting for us to try and understand whether we can enable a more and more autonomous behavior on the side of the robot. And in that sense, it becomes crucial to identify what could be an internal drive for the robot. And so we are experimenting with internal drives that are inspired from an affective perception. So even from, let's say, rebuilding a sort of an hormonal dynamics within the robot architecture, so that the robot, let's say, decides by itself what to do as driven by its internal motivation. And another important element that I would like to put on top of this discussion is that if we really believe that human awareness is important in order to allow adaptation and personalization, then maybe in certain cases, even the basic learning mechanism could be rethought to take into account a human or social dimension. For instance, considering within reinforcement learning elements related to a very human construct like rivalry, instead of just maximizing performance or minimizing the time or the, let's say, effort in achieving a certain result. And we have developed in collaboration with Pablo Barros, like scenarios and both simulation and interactive environment, where to try and explore the possibility for agents in reinforcement learning to be built by taking into account also this human aware dimension before pushing them to real interaction again with the robot. And what we are exploring now is really to try and find architecture that could allow, let's say, adaptation and personalization over different temporal landscapes, temporal horizons. So the ability for the robot to sense in real time and provide feedback in real time about, for instance, the performance and the state that this person is living at the moment. Here you see ICAP trying to teach yoga, for instance, but also the ability to build a representation of the person that lives over time. And so being able to recognize and re-recognize the person, being able to understand what this person's personality, attitude, and preferences were in order to create a very personalized, in a sense, teaching scenario for this. With this long series of slides, I think I clarified at least my perspective on what it means to have robots that are humanized to all humans, which are the steps that we need to make to add on top of that the dimension of personalization and adaptation. So with the cultural dimension, the personality dimension. I want just to conclude by mentioning why I think that's not the whole story. And this is related to, let's say, a debate that we had let's say, last year, I would say, with a very strongly multidisciplinary group involving philosophers, psychologists, economists, about what does it mean to have real human-robot shared experience. So if we want robots to actually be collaborators that share with us. And the take-home message that that to me comes out from this reasoning is that we have to stop or to move away from the tradition of looking with a human-centric view, but even with a robot-centric view. Because if what matters for us is really to have this possibility for interaction, what we need to start thinking of is really of the two and as a dynamic system. So how I am modifying the robot, so how my behavior can change the way the robot acts, and vice versa, how the robot can influence my behavior. And if you start thinking in this way, you realize that if you think of adaptation, of course, you can think it in a human-centric view. Oh, I want the robot to adapt because I want it to be compliant with my needs. But on the other hand, if you think of the dynamics, you realize that you don't want it to be too much adaptive. Because if the robot is too much adaptive, it becomes sort of a tool. It stops having its own identity. And without its own identity, we start missing, as humans, the possibility to predict it, the possibility to understand or have a guess of what this autonomous agent will do. And this is scary on the one hand. And if instead the adaptation is even to the point that it really becomes a tool so that I can predict everything about it, it becomes incredibly boring. So if we don't take this, let's say, the right stance, then the entire problem of description of an identity can lead to problems in the context of human-robot interaction, especially if we move away from one-shot interaction, we start thinking of long-term interaction. And therefore, we started thinking also with Sarah Nkao, who's actually the person coming from a philosophical background who's helping me in starting to consider these issues. What do we need? How can we operationalize a definition of artificial self or identity that could help us to avoid falling in this issue? There is a lot of literature in robotics actually asking about how to provide a robot with a sense of self. But what we realized is that often the focus is related to a sort of bodily self or the possibility of action that the robot has, which is of course a crucial component, but it's maybe not the whole story. And so, drawing inspiration from the work by Gallagher and Neisser, Sarah started proposing a vision of self, which is mostly focused on the idea of the flow of experiences accumulated in life, and then that tied together actually become an identity and a distinctive feature for an agent, in this case for a robot. And starting from this assumption, she was proposing, let's say, 4 operational components that a self should entail, starting from a spatial persistence, so the physical reference point for which every physical event concerning us originates, a relational nature, the fact that we are always in relation with someone else, and this happens already before we are born, when we are still in the womb, and the temporal persistence of the self. So the fact that we maintain a coherent image of ourselves in face of all the changes and of all the events that occur to us. And this is, let's say, temporality is what gives us identity to our eyes and also the eyes of others. And last but not least, as it's strongly interracially linked to all the 3 elements, is the metacognition. So the ability to conceptualize our experience of the world and our experience of ourselves. And so we believe that being able to model, to capture at least partially these 4 components of the self within a robot, within a cognitive architecture of a robot, is an important challenge that in turn has the potentiality of benefiting human-robot interaction as large. But of course, it's a work for the future. So to conclude, let me just recap a bit what this long presentation drove you through. So what I wanted to underline is the importance of having robots that are adapt to different levels. So they first need to be adapted to humans. And by that, we need to study how humans perceive and understand the human cognition and try to port it onto the robot. But then we need to endow them with the ability of adapting by themselves, autonomously, learning through the interaction with the partner to get the inter-individual differences and the dynamics of the state that each individual brings in. But last, this kind of cognitive architecture will also need the possibility to maintain a stability within, thanks to memory, thanks to internal motivation, so as to create a situation in which you really have an interaction with another agent and not just the mere use of a complex tool. This, I think, is the core of the cognitive robotics field, to really allow a robot to learn, to predict, but also to have memory and use it properly. And if this kind of topics are of your interest, I warmly suggest you to join the ICOG initiative, which is an open initiative started last year in IIT, but really open to the whole world. As you can see, there are already multiple participants, and in which we are really discussing how to advance our knowledge of human cognition by building and sharing a cognitive architecture for an embodied artificial system. And if the topics of cognitive robotics is interesting for you, then I also warmly suggest you to have a look at the IEEE RIS Technical Committee for Cognitive Robotics. It is our mission actually to foster the links between the field of robotics, cognitive science, artificial intelligence, as the PERSEO network is strongly doing, I would say, and also to make this field relevant from a social and an industrial perspective. So we are now about 200 members, and of course, if there are people interested in participating and working toward this mission, we are very happy to have you as members as well. With that said, I want to thank you for your attention and thank all the beautiful folks who actually made all the work I was mentioning today. Thank you very much.